Hello, welcome to Module 3, Video D. This is all about performing linear regression using the Statsmodels package in Python. So, above in the code, we've already imported the Statsmodel package, and we've defined our data frame model_df. And we've got all our variables in the forms that we want them to. So now we need to split it into y and x so that we can do our modeling. So for y, I'm going to go ahead and pick out medv. That's what we're trying to predict. And then for x, I'm just going to go and drop medv and keep all the others. So we'll run that, and now we've defined our x and y. Now next, in order to fit this model, we first need to tell it that we want an intercept, which is just, a term that doesn't have a predictor variable added onto it. So to do that, we do x-intercept, and we use this sm.add constant. Sm is what we imported Statsmodules as. And now we are going, and here I'll just show you this really quick. If I come look right here at what x looks like, it had 13 columns. If I look at what x-intercept looks like, it has 14 columns. So it's added this constant columns of all ones. So that's what happens right there. We add the x-intercept, and then we create the model with this statement right here. So it's sm, which again, that's our what we imported Statsmodules as, .ols, which is ordinary least squares regression. We give it our y, we give it our x, including the x-intercept, and then we tell it to fit. So that creates the model. It stores the model in our variable called model. And now we're going to print a summary of the model. So summary of the model is going to give us the model statistics, as well as our coefficients. So this is what the whole summary looks like. There's a few things that we want to kind of focus on that I'll point out here. So first of all, this is just kind of some basic information right here. And then right over here, this reports the r-squared value. So r-squared is a measure of how well our model is fitting the data. Specifically, it's a measure of how much variance our model is explaining. So in any data set, we have what we call variance, which is pretty much just the fact that not everything is the same. So medv, which was what we're trying to predict, not all values in medv are the same. They have a distribution. That distribution has variance, how much it varies, how different points are from each other. What r-squared looks at is it looks at the amount of variance which our model explains over the total amount of variance. And that ratio is our r-squared. So what this 0.79 is telling us is that our model is explaining 79% of the variance that is found in our response variable in medv. So, this isn't, obviously, it's not perfect. This model doesn't explain all of the variance that's going on in medv, but does explain a decent amount of it. That's not a bad r-squared value. There's also a few other variables it gives you right here. Sorry, not variables. Wow. Brain fog. A few other statistics. If you're interested, you can look more into these. We just won't be going into in this video. And then down here, what it actually shows you is the predictor variables and their coefficients. So the first thing it lists is the constant. That's what we added. So this is our x-intercept. So we have a x-intercept of 64.17. And then right here, it is showing us all of the coefficients for our predictor variables. So what we're actually going to be able to do is from this, we can build our model equation, which is what I've done down here. And actually, I tweaked some things since I last ran this. So some of these numbers aren't going to match exactly. I'll fix this before I upload it and put it on GitHub. So if you're looking at the version there, it will be correct. But pretty much what we do to build our model equation is it's med v equals, we have our intercept, and then we have each coefficient multiplied by the variable it belongs to. So we'd have the negative 1.19. You can see this time I ran it was a little different. But yeah, negative 1.19 multiplied by that crim variable. Except we remember that we did a variable transformation on crim. So it's not the coefficient just times by crim, it's the coefficient times by the natural logarithm of crim plus 1. And we can go through and we can put our whole model equation together like that. Just one more thing that we want to look at here in the summary statistics that it prints out is this p-value. So our p-value is a measure of significance. What it actually interprets to is the likelihood that you would see the coefficient you're seeing just due to chance. So if the p-value is high, that means, hey, the model's giving you this coefficient because it needs to give you a coefficient, but the coefficient isn't really meaningful. We could easily have just seen this coefficient due to chance. So for example, right here with Zn, we have a high p-value of 0.25 pretty much. So that means that there's a 25% chance that you would see this coefficient or something more extreme just due to natural variation in the data. So generally, in statistics, we look for p-values that are less than 0.05, so less than 5% of a chance that this is just kind of noise in the data, and that's what we see as significant. So next video, we'll be talking about a little more about model selection and get more into that, but here's the basic model that we fit.